October 29th, 2025. For months, astronomers had known this date would be important.
The object known as 3I Atlas.
The third confirmed visitor from beyond our solar system was approaching Perihelion, its closest pass to the Sun. Every telescope capable of observing it, from orbiting space observatories to mountaintop facilities, was pointed in its direction. What happened next would challenge decades of astronomy and remind humanity how small our understanding of the cosmos truly is. At precisely 0312 Universal Time, the object entered the critical phase of its orbit. 3I Atlas was expected to brighten modestly as the Sun's radiation sublimated volatile materials on its surface. Instead, it erupted in brilliance. In less than a minute, the object flared by over 4 magnitudes, a brightness increase by a factor of 40. Its faint gray outline transformed into a blazing white beacon against the star field. Across observatories worldwide, detectors saturated instantly. Photometric readings spiked off the charts. Even instruments not aimed directly at it recorded a sudden surge in light scattering through the solar plane. Something had happened, something that no known natural model could explain. The data arrived simultaneously from multiple sites across both hemispheres: Australia, Chile, Japan, South Africa. Every location recorded the same event at the same second. This global simultaneity ruled out instrumentation errors or atmospheric effects. The brightening was real, and it was universal. In the hours that followed, astronomers began a coordinated analysis of the raw data. The flare's energy output, derived from the integrated light curve, suggested a release equivalent to over 10 to 18 joules, comparable to the detonation of a large thermonuclear device. But there were no shock waves, no particle bursts, no ultraviolet flash typical of explosive outgassing. The energy release was purely radiative, perfectly symmetrical, and faded with unnatural precision. Within 10 minutes, 3I Atlas had returned to its previous magnitude, as though nothing had happened. To understand how extraordinary this was, one must understand what comets normally do. When a comet approaches the Sun, solar heat sublimates surface ice, venting gas and dust into space. This process forms the coma and the long, luminous tail. These emissions are chaotic, driven by irregular surface heating. A comet's brightness typically fluctuates over days or weeks, not seconds. But 3I Atlas had just brightened 40-fold in less than one. There was no precedent in the entire record of cometary science. As the initial shock faded, larger telescopes began collecting high-resolution images. The European Southern Observatory's Very Large Telescope captured frames revealing that the object's nucleus was no longer singular. It had divided. Multiple fragments were visible, moving outward from a common center along a perfectly straight axis. At first, it was assumed the comet had disintegrated, a common fate for small icy bodies near perihelion. But further analysis complicated that assumption. The fragments were not dispersing randomly. They were maintaining constant spacing, separating in an almost geometric pattern, each fragment equidistant from the next. The motion was steady, controlled, and symmetrical. Natural fragmentation produces chaos, tumbling shards, uneven dispersion, plumes of gas. Here, the structure was disciplined, even elegant. By sunrise, spectroscopic readings began to arrive from observatories in South America and Europe. The spectra contained none of the usual water or carbon monoxide signatures typical of comets. Instead, the light was dominated by nickel and iron emission lines, elements that vaporize only at extremely high temperatures. The ratio of nickel to iron, roughly 0.74, was consistent across independent measurements. No known comet in the solar system exhibits anything close to that composition. Ordinary comets are mixtures of silicate dust and frozen gases, fragile snowballs. 3I Atlas was behaving more like a metallic asteroid heated from within. Its reflectance spectrum resembled that of a solid, dense alloy, not a porous, icy nucleus. This single observation overturned decades of cometary models. If 3I Atlas were truly metallic, it could not have formed in the outer regions of a star system where volatiles dominate. It must have originated closer to a parent star, perhaps from a region where metals condense and ices cannot survive. Or more disturbingly, it might not have formed naturally at all. By late October 30th, the Hubble Space Telescope released its first post-flare imagery. Where a diffuse coma should have surrounded the nucleus, none existed. Instead, a concentrated glow extended forward in the direction of motion, like a headlight piercing the void. The illumination was spectrally pure, white with a faint blue edge, unlike the broad, dusty scatter of normal comets. Its orientation suggested something projecting or radiating from the front, not reflecting sunlight from behind. Scientists described it as a forward-facing emission, a configuration for which there was no known natural analog. The metallic nature of the fragments deepened the mystery. At 136 astronomical units, solar heat could not melt or vaporize nickel or iron. For such elements to produce visible spectral lines, temperatures would need to exceed 2000 Kelvin, far beyond what solar radiation could induce at that distance. Yet the data was consistent across observatories. Either the object contained internal heat sources or was interacting with the solar environment in an unknown way. NASA's Parker Solar Probe and the European Solar Orbiter were both monitoring solar activity at the time, though their official reports have not yet been released. Leaked telemetry suggested that the probe's magnetometers detected a transient magnetic field disturbance coinciding with the flare, small but distinct from normal solar variation. If true, this would imply that 3I Atlas momentarily emitted or interacted with magnetic flux strong enough to register tens of millions of kilometers away during its passage around the Sun. The object should have developed a long tail extending away from the solar wind. But imagery from both ground-based and orbital observatories showed no such tail. Instead, a faint symmetrical halo extended equally in all directions, again inconsistent with the physics of solar wind pressure. The material surrounding it appeared to be not gas or dust, but particulate metal vaporizing in controlled release as it curved along its outbound path. The brightness did not fade as rapidly as expected. Its surface reflectivity remained unusually high, as though the object was maintaining a constant temperature or illumination independent of solar angle. The more data arrived, the more 3I Atlas defied classification. It was not a typical comet, not an asteroid, and not consistent with known interstellar debris models. Its metallic composition, symmetric fragmentation, magnetic anomaly, and controlled emission pattern each contradicted standard astrophysical behavior. And yet the data was consistent, reproducible, verified by multiple independent observatories across continents. For those who remembered the history of interstellar visitors, the parallels were hard to ignore. In 2017, Oumuamua, the first known object from beyond the solar system, had also exhibited unexplained acceleration without any visible outgassing. In 2019, 2I Borisov followed, a more typical comet. But 3I Atlas combined both mysteries: the speed and trajectory of Oumuamua, the shape and luminosity of Borisov, and the metallic composition of neither, the cosmic trifecta of anomalies. When the flare occurred, the Parker probe's solar environment readings registered no corresponding solar event. No flare, no coronal mass ejection, no radiation burst capable of causing the brightening. The Sun, in short, had done nothing unusual. Whatever caused the flash came from the object itself. Theoretical physicists proposed natural mechanisms, none entirely satisfactory. One hypothesis suggested a sudden collapse of internal cavities under thermal stress, releasing energy through frictional heating. Another posited piezoelectric discharge through crystalline metal grains. But none explained the perfect symmetry, the precision of timing, or the rapid decay of brightness. Some speculated about artificial origins, an idea quickly dismissed in official circles but not forgotten. The term controlled energy release began to appear in preprints, though rarely in final publications. The timing of the event added another layer of intrigue. When traced backward, 3I Atlas's trajectory intersected the region of sky from which, nearly half a century earlier, the 1977 WOW signal had originated, a narrowband radio transmission at 1420 MHz, the hydrogen frequency. For decades, the WOW signal had remained a singular enigma in SETI research, powerful, narrow, and never repeated. Statistically, the alignment between that historical signal and the current path of 3I Atlas is roughly 0.6% probable by chance. To scientists, it is coincidence. To others, Perhaps not. As the comet completed its perihelion arc and began its long outbound journey, the brightness gradually stabilized. By mid-November, it was once again too faint for most telescopes, retreating toward the outer regions of the solar system. But its data legacy remained immense, terabytes of imagery, spectra, and telemetry that will take years to fully analyze. Official statements from NASA and ESA have been cautious. They acknowledge the flare, the fragmentation, and the anomalous spectral data, but stop short of conclusions. Their language is measured. Non-gravitational acceleration under review, compositional variance observed, further modeling required. In the restrained language of science, these phrases carry weight. They mean